Good morning, dear students. Welcome to another session of microwave and antennas. So in the previous session, we started our discussion with respect to loop antennas, in which we had a discussion regarding what is meant by loop antenna. And then we came across how do you classify the loop antennas as a small loop or a large loop? So there were two conditions what we had checked out. One was the ratio C divided by lambda. If it is very much less than 5, it will be classified as a small loop. If this condition is not satisfied and it turns out to be C by lambda is greater than 5, then we classify it as a large loop. So this is one condition where we had come across regarding the loops. And we had observed that the circular loop, we can represent the same in the square loop form. And what we do is we can consider these sides as the dipoles, And based on that, we did an estimation of what is the field pertaining to these aspects. And this is the orientation what we were considering. Now, if you change the orientation, suppose you make this as Z axis, then this as Y. So there'll be changes in the parameters. So we should be considering those aspects also. Now, based on this specification, the field values remains the same. Only the unit vectors and other stuff, right? Those will be changing. So based on this, we identified what is the field for a small loop. What's the field for a small loop? So based on this, we obtained the final field value for the small loop, which was given by this parameter. It was given by this parameter. 120 pi square retarded current sin theta divided by r into a by lambda square, where a is the area of the loop, lambda is the operating wavelength, r is the distance at which you are measuring the field. This I, what is present in the bracket, is the retarded current. So these are the things what we had obtained, and h theta is obtained using E phi divided by 120 pi. So we obtain this result for magnetic field, which is in the theta direction. So then we observed the comparison of the fields with respect to small dipole and the short electric dipole. So that is the Hertzian dipole. So these equations are referred from the previous sessions. So in this case, based on the orientation, if you remember for dipole, how we had obtained, we had placed the dipole along the Z axis, and at a distance r, we were measuring the field. So with respect to this, we obtain E theta and H phi components in electric dipole. For small loop, what happens is we obtain E phi and H theta components. So these are again related to far field parameters. So next we discussed regarding the loop antenna as a general case. So in this, we considered a circular loop, and on that we considered a small elemental length of A into d phi, and we considered two elemental lengths which are opposite to each other, and we applied the dipole concept, and then we obtained the field representations for this parameter. So when we when we consider this, right, and we place it in the dipole form, this is how it will be represented. So these are the A d phi components, that is the small dipoles, and this is the radius of the circle or the loop what we are considering. So when we rotate this and we place it, we can observe that this is how it turns out to be. And when we try to measure this path difference, it turns out to be 2 times beta A cos phi into, actually it is sin theta. It is sin theta, which is nothing but the path difference in terms of the angular specifications. So this is the parameter what will be used in case of the loop antennas in the general case. So, and we observed that we started off with the vector retarded potential. This is the vector retarded potential, which is the elemental parameter. And from that, we obtained what is the overall representation for the field, using which equation we used this equation, which we had seen in the previous case of when we had obtained the results for the dipole. That is the short dipole what we had observed. So how we can obtain the field when we have vector retarded potential and scalar retarded potential. So from that parameter, we have obtained this value. So and we made use of the Bessel function in which is of the first order, and the parameter with which the Bessel function is defined is beta a sine theta. So this is the field which is due to the loop in general case. So based on this, we had tried to see what is the field parameters for the small loop and the large loop, and using those, right, we obtain the radiation resistance. So again, in this case, what we do is, in order to obtain the radiation resistance, first we try to obtain what is the total power that is radiated by the antenna which is under consideration. So in this case, it is the small loop what we are considering. Say in general, any antenna what you're considering, it is taken, it is given by the double integral of the power density, which is integrated over ds, where ds is what? R square sine theta d theta d phi. It is R square sine theta d theta d phi. So first you obtain the total power using the power density. So in this case, what we do is we make use of the average Poynting vector or the average power density, and then we obtain the total power which is being radiated. And then we obtain the total power radiated in terms of IRMS into RR, that is radiation resistance. Then we equate both and obtain the value for RR. So this method will remain same for whichever radiation resistance you are obtaining. So for whichever antenna you try to obtain the radiation resistance, this step remains same. So previously I mentioned that C by lambda, if it is less than pi, you classify it as a small loop. There is another condition what you can use. If the area of the loop is lesser than lambda square by 100. So this also classifies the loop as small loop. If both these conditions, if this condition and this condition fails, then we classify it as a large loop. So in a previous session, we had obtained what is the radiation resistance of the small loop. So again, in this case, what we had done, we had obtained what is the total power radiated when I know what is the average Poynting vector. Average Poynting vector, or sometimes we denote it as SR. So that is substituted over here, and you simplify this parameter, and what we obtain is so when we simplify the entire parameter, we obtain the total power from the Poynting vector or the say average Poynting vector or the power density, which is given by equation 9. And similarly, if I go ahead with the radiation resistance, I obtain the total power radiated, which is given by equation 12. And when we equate both the equations, that is equation 9 and equation 12, we end up with radiation resistance for the small loop, which is given by equation 13. And in the majority of the cases, what they specify is the radiation resistance of the small loop is given by 31,200 into A by lambda square, the whole square. So and so this was considered when there was only one turn. So if I have a loop antenna which is having several number of turns, say n number of turns. So in that case, what happens is the total area what we are considering will be equal to number of turns into area of one loop. So therefore, the same equation will be represented over here as equation 16, in which you are considering there are n number of turns in which each turn is having, or each loop is having an area of A. So it will be n into A divided by lambda square, the whole square. So this is for n equal to 1. This is in general for the small loop. So now moving further, when we consider the large circular loops. So again, we need to continue with the same method. So first what we do is we try to identify what is the, this is nothing but in some notations it will be SR. So this is the average Poynting vector, what we are considering, or the average power flow, power density, which is given by half into E phi. This is H theta. This is H theta. E phi cross H theta, and it is complex. It is. So now let us have a look at what is the radiation resistance of the large circular loops. So again, we consider the average Poynting vector, that is SR, which is given by half into E phi cross H theta, it's complex. So when we simplify this parameter, we end up with this equation, that is half into magnitude of H theta, it's square, into 120 pi. So this is again based on the previous discussions. So what we had, that is we simplify E cross H phi. So when we obtain this, so this is the equation what we'll be getting when we simplify it. It is 60 pi into magnitude of H theta, it's square. So now what is H theta? So for this case, right, we make use of the general case of the loop antenna. We make use of the general case of the loop antenna. So for that, what was the fields we had obtained? We had seen that H theta was given by this equation, which is beta into A into retarded current divided by 2 times R. This is the Bessel function of first order, which is beta which is related to the parameter beta A sine theta. So now when we take the magnitude of this, what we have, when we take magnitude associated with this, so we have magnitude of beta, in that is, it will be beta into A, and this one is, if you remember, it is I naught into e raised to j omega t minus r by c. It is t minus r by c. So therefore magnitude of this parameter is equal to I naught divided by 2r, and the magnitude of this parameter is same, j1 in j1 of beta a sine theta. So now when we substitute this parameter in the above equation, that is in this equation, when we substitute it in this equation, we end up with the average Poynting vector or the power density as 15 times pi into beta a into I naught its square divided by r square. It is j1 square, that is Bessel function of first order, its square, in which the parameter is beta a sine theta. So now we make use of one of the properties of the Bessel function. So in this case, what we do is we obtained the average Poynting vector, or what we are specifying as RMS value of the Poynting vector. So now if I want the total power, right, sometimes we denote it as W. So in this one, what we do is we double integrate this with respect to ds. We double integrate this one with respect to ds. So that is what we are doing here. We are trying to obtain what is the total power which is being radiated by the antenna which is under consideration. So when we move further and try to simplify it, this is the result what we'll be getting, in which you can observe that this is associated with sine theta. And this overall parameter, when we consider, what happens is based on some property, we can simplify this integration. So in the end, what we have 15a beta a into I naught its square, r square and r square gets cancelled. So that r square term is gone off. Integration of d phi with the limits of 0 to 2 pi, and integration of j1 square beta a sine theta d theta, the whole square it is. It is actually the integration whole square. So now what we do is, sorry, it is not the whole square. It is just j1 square. So I'm just, it is just this much. It is not the square. So here what we have 15a beta a I naught square. This phi integration of d phi is nothing but phi with the limits of 0 to 2 pi. And here what we do is, to simplify this, we make use of the property of the Bessel function. So what is the property of the Bessel function? This is the property what we will be utilizing. So here what we have, if we have j1 square, here we have the x parameter x into sine theta. This Bessel function multiplied with sine theta, its integration with respect to d theta. This one can be written as 1 by x. So this x value is, which is present within this brackets, integration 0 to 2x j2 of y. So here this is the Bessel function of second order. So when we apply that concept, what we have is, we can observe here, beta a is x sine theta into sine theta d theta. So when we apply this, what we end up is, we end up with this parameter in the simplified form. Now what happens is, 2 times beta a is actually equal to 2 times c by lambda. It is again obtained from the geometric specification. It is obtained from the geometric specification. So therefore, what they have done is, they have replaced 2 times beta a in the integration with 2 times c by lambda over here. Now, so this is the parameter what we are obtaining for the total power which is being radiated when you're considering the field parameter. So in this case, I considered s theta and we obtained the equation 26. So now what we do is, with respect to radiation resistance, we try to see what is the total power which will be radiated, which is given by IRMS square into RR. But what is IRMS? It is I naught divided by square root of 2. Therefore, the equation gets simplified to I naught square divided by 2 into radiation resistance. Now what we do is, we equate equation 26 and equation 27. So when we equate this and we simplify, we obtain a radiation resistance which is given over here, wherein the radiation resistance of the large loop is given by 60 pi square into c lambda. Now this is nothing but sorry, c by lambda integration 0 to 2 c lambda j2 of y with respect to dy. So this is what we will be getting. So now based on c by lambda value, right, this integration parameter will be changing. So what we have is, so we see that for large loop, right, the condition is c by lambda is greater or equal to 5. So this is the condition what we had observed. So if c by lambda is greater than equal to 5, then we consider it as the large loop. And in this case, say we are considering n is equal to 1, that is one loop. So if that is the case, what happens is, this integration what is there, it equates to 1. It equates to 1. So therefore, when we try to solve this problem, what happens is, we get radiation resistance for large loop equal to 60 into pi square into c by lambda. So this is the radiation resistance of the large loop when we consider there is one turn and it is a large loop. So this is the radiation resistance. So here we observed what is the radiation resistance of the large loop when we consider there is only one turn. So this is associated with the radiation resistance. Now here we can observe that what happens if c by lambda keeps on increasing. Say from 0 to 10 they have seen. So what happens is, it keeps on increasing initially in the linear form and then it starts to decrease by some amount, and when it is again 5, right, it slightly increases and tries to retain its value. So this is the radiation resistance which is seen with respect to the large loops. So this is giving you for small loops. This is giving you for the large loops. So you can observe that for large loops, what happens is, radiation resistance is greater as compared to the radiation resistance of the small loops. So this is what we can observe from the graph over here. Now, what is the directivity of the antennas, which is a small loop? So the directivity of the small loop antenna is given by 1.5, and whereas for the large loop, right, we have directivity which is associated with c by lambda value. So here directly it is a constant value, but for large loops, right, it turns around for equal to 4.25 into c lambda. And if we try to simplify this in terms of the radius of the loop, so c is the circumference and a is the radius of the loop. If this is the case, and this entire this thing, if I consider, it is the circumference which is given by 2 pi a. So when I try to simplify it, it will be around 0.68 times a by lambda. So this is what we are getting for the directivity of the circular loops. So these are few of the applications of the loop antennas. So wherein the loop antennas are basically utilized as a source for the paraboloid. Paraboloid is nothing but you have observed the dish antennas, right? How they'll be like a saucer kind of structure. There'll be a saucer kind of structure, and in front there'll be a feeder or a receptor. So what this does is either it receives all the signals which are falling onto the parabolic structure. So in such cases, you try to make use of the small loop antennas. Then apart from this, when we want to have a line of sight communication, that is in a straight path. So if I have, say, two towers, if I have two towers and I want line of sight communication between them. So for those purposes, you can look out for using these loops in you can use this loops for the communication, because what happens is in many of the cases the earth surface is curved. So what happens is you might see that one antenna might be here and one antenna might be here. So these cannot have line of sight because of the curvature. So because of which we go for ionospheric propagation. That is, we make use of the ionosphere, that is the layers of the atmosphere, in order to transmit the wave from one end to the other end. In this way, we try to increase the distance of line of sight. So because of which we are talking of line of sight over here. Then apart from that, we can see that we can have different kinds of structures. So here we can see that this is a loop antenna, which is in clover shape, clover leaf. And this one is the alphard loop, so which is designed in this form. So each of them have their own specifications. Then another important thing is the direction finder for which the loop antennas are used. So these are a few of the applications pertaining to the loop antennas. Okay, let us have a look at a problem pertaining to loop antenna. So here we have the radius of the circular loop antenna is given as 0.02 lambda. How many turns of the antenna will give a radiation resistance of 35 ohm? So what does the problem specify? That it wants a radiation resistance of 35 ohm. So for this purpose, how many number of turns would be required for the loop? And it is specified that radius, that is in this case A. So as we had seen, A is the radius of the loop antenna. A is given as 0.02 times lambda. So now here what we need to do is first we need to identify whether it is a small loop or a large loop, because radiation resistance for small loop the equation is different and for large loop the equation is different. So here what we need to do is first we need to identify C by lambda, or you obtain what is A, whether it is less than lambda square by 100. So either this or that. So what we do is we'll consider C by lambda over here. So what is C? C is 2 pi by A, 2 pi into A, and it is divided by lambda. So when you substitute A, you obtain the value of C by lambda as 0.1256. Now, whether this value is lesser than 5, so we can observe that it is much lesser than 5. So therefore, what does this imply? This implies that the loop is small loop. So therefore, what is radiation resistance of small loop? Radiation resistance of small loop is given by this equation, where is RR is equal to 31,200 A into N divided by lambda square whole square. Now, what is a main case? I have to identify how many number of turns are required for this case. So when I simplify this equation and try to solve for N, right, I'll be obtaining N as 710.2. Sorry, N square as 710.2. And when we take the square root, we get it around 26.65. So I cannot have a fractional value for this. So what we do is we equate it to the next nearest value, that is 27. So here number of turns which are required to have a radiation resistance of 35 ohm is 27, and this is obtained for what? For the small loop what we have considered. So similarly, let us have a look at the other problem. Determine the directivity of loop antenna which is having a radius of 1 meter. So here is given A is equal to 1 meter when it is operated at a frequency of 0.9 megahertz. So here we need to identify what is the directivity. So again, first identify what is C by lambda, whether it is small loop or large loop. So since frequency is given, from this I can obtain what is lambda. Lambda is given by C divided by F, where C is the speed of light what you are considering in the vacuum. So when we obtain C by lambda using this equation, what we obtain it as 0.01885, which is very much lesser than 5. So therefore, what does this specify? This specifies that it is a small loop. And for small loop, we had identified that the directivity is a constant, which is 1.5. So therefore, we got to know that the directivity of the antenna, which is specified here, is nothing but it is equal to 1.5. So if suppose if it was a large loop, then we had to use the other equation what we had observed. So these are the two examples or two problems pertaining to identifying the number of loops and pertaining to identifying the directivity. So if So Babinet's principle is basically used to identify what is the field due to a say complementary antenna, when we know what is the field which is present due to the opposite that is the antenna which is opposite to that complementary antenna. So here what we are doing is here we consider a source and here we consider a observation plane. Say this is the screen. So and in front of this, say we have a screen, that is this is the observation plane, and we have a screen in front of this. So here when we observe what are the field lines, right, we'll be observing that this will be observing it in this form. So here if this field what we obtain, we represent it as fs1. And if I consider the same source and I remove this antenna and replace it with its complementary part, that is, here there was previously a screen present. Now in this part there is no screen, but at the other part there is a screen. So we get, when we observe the fields right over here, we get the complementary field over here. Now we consider the third case in which we have a source and we have no screen at all. So it will be like the total field which will be present. It will be the total field which will be present. So therefore, how they represent it is the field which is obtained at a point XYZ on this observation plane. So I'll be considering one point on the screen. So when the screen is present, we obtain the field as Fs, which is represented, say, F1 of X, Y, Z. Now, similarly, in the next case, what we do is we consider the field which is due to complementary version of the previous case, that is the complementary field parameter. So at the same point, so if we consider one point over here, at the same point, we try to measure what is the field value. So we'll be getting complementary field, which is given by FCS, which is equal to F2 of XY, Z. Now what happens is when I try to measure the field when there is no screen, it should be actually equal to field due to the screen plus field due to the complementary screen. So this is the concept of Babinet's principle. So therefore, if we have a field that is without the screen at point XYZ, when I measure it, it is given by F3 of XYZ. So therefore, based on the Babinet's principle, what happens is this F0 field, that is F3 of XYZ, is nothing but it is equal to field due to the presence of the screen plus field due to the absence of the screen. That is the complementary version of the screen. So which is given by this parameter. So these are basically used to identify the fields which are presented due to the complementary version of the antennas which are under consideration.